Welcome to this video on perturbation theory, a method for quantum mechanics estimation. We will explore how this powerful tool helps us solve for systems in our universe that are too complex for exact calculations. We can solve the Schrödinger equation exactly for simple systems like the hydrogen atom. However, real atoms exist in complex environments, making exact math impossible. Perturbation theory allows us to find high-accuracy approximations for these real-world, almost ideal systems. Imagine a perfectly still lake as an ideal system. When a tiny pebble is thrown, the resulting ripples are small corrections, or perturbations, to the perfect stillness. In physics, a perturbation is a new energy term that is much smaller than the original energy. Our mastery roadmap involves two main parts. First, the setup, where we define the split Hamiltonian and power series. Second, the derivation, where we calculate the first and second order corrections. We begin with part 01. The mathematical setup. This involves strategically dividing the total energy into parts we know and parts we need to solve for. We define our total Hamiltonian H as the sum of H0 and H prime, where H0 is the solvable part and H prime is the small perturbation. We introduce the small parameter lambda to track the size of this perturbation. We assume that the solutions for the zero-order system, H0, are perfectly known. Our main goal is to determine how the energy En and the quantum state psi n change when the perturbation is applied. The core of this method is the power series guess. We assume the new energy can be written as the original energy, plus a series of corrections. As lambda gets smaller, the higher order terms quickly become less significant. Similarly, we expand the perturbed wave function as a sum of the zero-order state and subsequent corrections. The first order correction, psi n1, shows the most significant shift in the wave function's shape. Now we move to part 02, the derivation steps. Here we use logical steps to isolate and solve for the energy and state corrections. Step 1 is assembly. We plug the full expansions for the Hamiltonian, energy, and state into the master Schrödinger equation. This generates a large equation where terms are multiplied by different powers of lambda. Step 2 is grouping. We collect terms that have the same power of lambda. Focusing on lambda to the power of 1 gives us the equation containing the first-order corrections. Step 3 is finding the first-order energy. We multiply the first-order equation by the bra of the zero-order state. This sandwiching trick uses orthonormality to simplify the equation, isolating the energy shift En1. This reveals the master formula for the first-order energy correction, E1. It is simply the expectation value of the perturbation Hamiltonian H prime in the original unperturbed state. This first-order correction means the system stays in its original shape, and the energy shift is the spatial average of the extra energy it experiences. Most observed spectral shifts are dominated by this single term. We now begin part 03, the wave function correction. We explore how the shape of the quantum state itself is distorted by the perturbation. The correction to the wave function, psi n1, can be expanded as a sum of all other unperturbed states. The coefficients Cm tell us exactly how much of each state is mixed into our original state by the perturbation. Substituting this sum back allows us to isolate the mixing coefficient Cm. This amount of mixing depends on the perturbation's matrix element and is inversely proportional to the energy difference between the states. The first-order wave function shows how the perturbation distorts the state. It borrows components from other allowed states to adapt to the new energy environment, defining our perturbed reality. Next, we look at part 04, second-order energy. This correction refines the precision of our calculation significantly. The second-order energy shift, E2, is derived from the terms grouped by lambda squared. It physically accounts for the fact that the system is already using the distorted first-order wave function. The E2 master formula sums the interaction with all other states. Each term involves the square of the interaction strength divided by the energy gap. For the ground state, this correction is always negative. This correction shows state push and pull, meaning energy levels repel each other. The closer two states are in energy, the greater the distortion and repulsion they exert on one another. We proceed to part 05, validity and limits, discussing when perturbation theory breaks down. The rule of thumb for validity is that the perturbation strength must be much smaller than the energy gap between states. If two energy levels are equal or nearly equal, the math fails, and we must use degenerate perturbation theory instead. To recap our perturbation toolkit, E1 is the average of the perturbation. Psi1 involves the mixing of other states weighted by the energy gaps, and E2 is the sum of the squares of mixing divided by those energy gaps. A key application is the Stark effect, where an external electric field distorts atomic energy levels. Perturbation theory allows us to calculate the resulting spectral line shifts and splitting. We have reached part 06, the conclusion. We will summarize the quantum approximation engine we have explored. For a deep dive, the second-order correction to the wave function follows the same mixing logic, incorporating cross terms from the first-order shifts. This refinement provides sub% accuracy in demanding simulations. Another deep dive topic is normalization. We enforce that the overlap of the original state, with the first-order correction, is 0. This ensures the total probability remains 100%, meaning the perturbed wave still represents one particle. Today's focus was on non-degenerate systems, where energy levels are unique. If energy levels are shared, one must first switch to degenerate perturbation theory and diagonalize the perturbation matrix within that shared space. Perturbation theory also explains the Zeeman effect in magnetic fields. It determines how energy levels shift based on the interaction of the electron's spin and orbital motion with the magnetic field vector. The fine structure of the hydrogen spectrum, resulting from relativistic speeds and spin-orbit coupling, also requires perturbation theory for accurate description. To recap the core assumption, perturbation theory is the engine of quantum approximations. The total Hamiltonian is split, and the total energy is expanded as a power series in the perturbation strength. Perturbation theory shows that small changes in the environment lead to predictable, measurable shifts in matter's energy. We do not need perfect math to understand the complexities of the real world.